In this lecture, I will start the discussion of a spin dynamics. And the purpose of studying this problem is if this were a conventional quantum class or a class on condensed matter physics, the purpose of such a study would be to understand, just understand the literally the dynamics of spins and not much more than that. However, with the advent of quantum information, eventually we will try to go beyond that and use our understanding of the spin dynamics in order to have some control over the spin dynamics. In other words, we don't just sit idly by and watch as the spins evolve in time, but we want to force the spins to evolve in a certain way that's consistent with our idea of quantum computation. But like everything else in science and engineering, one first has to master the understanding of the problem before one can start to exercise any amount of control over that. Okay, so here comes the understanding part. And I'm going to actually divide up the discussion into two parts. And the first part is about the Zeeman problem. And the second part, which will be talked about in the next video, not in this video, is the Rabi problem. Okay, roughly speaking, the Zeeman problem is when the external magnetic field is static, namely the field direction and strength does not change over time, whereas the Rabi problem is the case where this is dynamic. Dynamics simply means that the magnetic field has a time dependent component, and in particular, we're going to be concerned with the case where the time dependence is harmonic. That is, it depends on time like a signed function. Okay, so why are we suddenly talking about the magnetic field? Well, the reason is because it is the magnetic field which couples to the spins. Okay, so here's some particle, most likely an electron, and electron has a spin half. So its a spin orientation is schematically shown as some sort of an arrow pointing along a certain direction in space. And you apply a external magnetic field by putting a magnet nearby. And this magnetic field will then have some influence on the way that the spins evolve over time. Okay. Since the evolution of any quantum state is completely governed by the type of Hamiltonian that it obeys, I'm gonna start with just writing down the appropriate Hamiltonian for the problem, And that's well known. And this sort of Hamiltonian is known as the Zeeman Hamiltonian, or the Zeeman term. It's named after a Dutch physicist who did important experiments probing the properties of matter under a strong magnetic field. And for his accomplishment, he was given the Nobel Prize in 1902. So actually, remarkable fact is that the first person ever to win the Nobel Prize in physics was Röntgen, who first discovered the X-ray, and the second person ever to win the Nobel Prize is actually this person, Zeeman. So he's actually a quite important figure in the history of physics. Okay, so why the electron spin would couple to the magnetic field in this way? Well, we don't know. It's just the way it is. So this is how spin interacts or couples with the magnetic field. Okay? And people have arrived at this realization through various means, both experimental and theoretical, in the around the 1920s, immediately after the discovery of quantum mechanics. And actually, to be completely precise, there has to be something called the Bohr-Magneton factor over here, just to make the dimensions consistent with the dimension of energy. But for convenience, I'm taking the Bohr-Magneton to be basically zero, to be basically one, so that I can work with this much cleaner looking Hamiltonian, and just focus on its solution. Okay, so here I'm talking about not just every two-level system you can imagine, but here in this case I'm talking specifically about the electronic two-level system, where the electron's spin is the one that's doing the two-level dynamics. Okay, so the Schrödinger equation then for this electron spin would be like this. Now, the meaning of these two coefficients, alpha and beta, would be the following. So here's a wave function which represents the state of the electron spin. So this is a wave function for the spin of the electron, but not for its center of mass motion. And it's given as the superposition of the spin up state and the spin down state. Okay? And all the time dependence, of course, comes from the time dependence of these two coefficients. Well, but actually, this is a problem that we have studied for quite some time. Okay, and we can actually write down the solution almost immediately, given all the experience that we have already accumulated from the exercise and the recipe that we have developed for solving the two-level problem. But let me propose a slightly more formal solution, just to broaden our horizon. or technical landscape. So this is a more formal expression for the quantum state psi. And in fact, although I did not emphasize this in my earlier videos, the solution of this problem is actually is quite straightforward to work out. It's this thing acting on some initial state. Psi 0. Okay. Well, to see that this is the solution of the Schrödinger equation, all you have to do is just to take the derivative on this, which will then only act on this exponential factor, which will then bring down the factor of h, like that. Then this is, by definition, psi at time t. So overall, we have these Hamiltonian acting on the psi t, which is precisely the Schrödinger equation that we were trying to solve from the start. Okay, so now the job is pretty easy in the case where the Hamiltonian is given by this, because then the state evolves according to this. Sigma dot b t and psi 0. Okay. Now, now there's this factor. Okay, and I'm going to write the magnitude of these of this magnetic field vector as some number omega, and I'm going to write its orientation as this unit vector n. Then this factor becomes e of I omega t multiplying sigma dot n. Okay, but from the previous video, we know that this exponential of the Pauli matrix has a much simpler expression, cosine omega t plus I sigma dot n multiplied by sine of omega t. Okay, so then psi of t is given simply by cosine of omega t plus I sigma dot n multiplying sine of omega t acting on the initial state. Okay, so this is the most general and complete solution of the Zeeman problem, or Zeeman Hamiltonian. All right. Okay, so now to further solve this problem, now we need to specify what we want to choose for the initial state. Okay, so remember that now n is really just the orientation of the external magnetic field. And if it happens that the initial state was along the was along these magnetic field, namely, if the initial state was in fact an eigenstate uh, like that, and remember, let's recall that this is an eigenstate of this Hamiltonian, sigma dot n. Okay, so in that case, then psi t becomes, now when sigma dot n acts on the initial state, it gives you back 1. So this is cosine omega t plus I times sine omega t acting on the initial state. But that's just this oscillatory phase factor. And we know that in quantum mechanics, this overall phase factor does not really do anything. It's just not changing the content of the physical state. So what was initially a state pointing along the direction of the external magnetic field will stay as such over time, and it's not changing its status. Of course, that's exactly what one expects from the state being an eigenstate of the Hamiltonian. And similarly, if the initial state was the other eigenstate, then you can easily show that the time evolution of the quantum state is E of minus omega t acting on the initial state. So again, there's no real change in the state over time because this is also the initial state, the eigenstate of the Hamiltonian that we chose to be the initial state. Okay, so those two are the boring situations. More technical terminology would be that these are the stationary states. Stationary states. However, a more exciting case is when the this time evolution thing does something more meaningful. Okay, so to make this story a little more interesting, we would have to choose the initial state to be something which is really a linear combination of the n and minus n. Okay. But in that case, the time evolution would give one kind of phase factor for the n state and the other kind of phase factor for the minus n state. And so then it will no longer be a simply n or simply a minus n, but as it will be a mixture of the two. Okay. So how do we really bring out its mixed nature? Well, we can bring that out by calculating, for example, the average of the spin operator, which will then pick up various terms. Let me just go ahead and do the computation myself. After all, this is pretty straightforward. Yeah, so you're going to find this term. Yeah, and then you're gonna find alpha, beta, star, star meaning the complex conjugate. And this kind of overlap, plus its complex conjugate. So that. Okay. So again, we have some component which is time independent. So nothing changes over time. But now, finally, we're starting to see some time dependent stuff. Okay, so how do we work this out? Mm, well, it depends on to work this out. You might have to specify the exactly the direction of this n vector. Mm, so what do we do? Let's pick some axis. Okay, so maybe the simplest choice we can make is to have the B field along the z-axis, so that the B vector would be 0, 0, B, and then perhaps prepare the initial state to be along the to be something like plus n minus n, so it's a equal mixture of the two states. So here n means really just 0, 0, 1 unit vector, and this, the wave function that represents such a coherent state is actually 1, 0. And you can verify this by explicit calculation yourself. And so in terms of explicit components, the initial state will be given by this. Okay, and then it's just a matter of doing these calculations, all these calculations explicitly, which will give you the following answer. And all of this is really a matter for you to work out. And what I find is this sort of thing, 1, I, 0, minus 2I omega t, 1 minus I, 0. And if you do some cleaning, then you find cosine 2 omega t and minus sine 2 omega t. Okay? Okay, so this is actually good because as promised, we have this initial spin pointing along the x-axis. That was the initial state. But now, now the magnetic field is directed along the z-axis. And now what happens is that this spin is rotating within the xy plane. Okay, so this is the x-axis, this is y-axis. And the sense of rotation is from x-axis toward the minus y-axis, so it will be rotating this way. In the yeah, it will be rotating like this. Okay, and this sort of thing is called a precession. And precession in the classical physics means that you have a certain axis, and then you have a certain vector, and then that vector kind of makes an orbit around the axis without either getting close to the axis or moving away from it. But it simply maintains a some fixed angle of inclination with respect to the rotation axis, and makes a circular motion around it. And such is what happens with the Zeeman problem. And what the Zeeman problem tells us is that with the applied magnetic field pointing in a certain direction, and you have a initial spin which is pointing at some angle from the magnetic field, then the initial spin will execute a precessional motion around the magnetic field as the rotation axis. Okay, so the Zeeman problem is nothing but the precession. The Zeeman problem gives you nothing but the precession of the spin around the Zeeman field, around the magnetic field. Okay, so that's the essence of the Zeeman problem. And the big difference with the Rabi problem is that there's a B static, and then there's a B dynamic. So the Rabi problem concerns the case where you have both a static magnetic field plus some magnetic field which is being applied in the perpendicular direction to the static magnetic field, and this perpendicular magnetic field has a explicit time dependence. Okay, so the Rabi problem is about the dynamics of a spin in the presence of these crossed magnetic field, one of which is static and the other one is dynamic. And I will discuss the solution of this problem in the next video.